Download this code from codegive.com, link in the description below. OK, let's dive into advanced socket programming topics using Oracle's programming interfaces, focusing on building robust, scalable, and secure network applications. This is a comprehensive guide with code examples and explanations. We'll cover these key areas. Asynchronous I/O and non-blocking sockets. Improving performance by handling multiple connections without blocking. Multiplexing with select, /poll, /epoll, efficiently managing multiple socket connections. Multithreading and multiprocessing. Using threading or processes to handle concurrent connections. Socket options, reuse dress, TCP_nodelay, etc. Tuning socket behavior for specific needs. Secure socket layer, SSL/TLS, sockets. Implementing encryption and authentication. Oracle specific considerations, if applicable. While Oracle DB connections are typically handled with dedicated drivers, we'll discuss scenarios where raw sockets might be used and the necessary security practices. Prerequisites. A basic understanding of C/C++ or other languages if Oracle libraries support them directly. Familiarity with socket programming concepts, IP addresses, ports, TCP/UDP. AC/C++ compiler, example GCC. Open SSL library installed, for SSL/TLS. Oracle client libraries, if interacting with Oracle databases via sockets, typically, dedicated Oracle drivers are used for DB interactions, but the principles of socket security still apply. 1. Asynchronous I/O and non-blocking sockets. The standard read and write calls are blocking. This means a thread will halt until the operation completes. For server applications handling many clients, this is a significant performance bottleneck. Non-blocking sockets and asynchronous I/O allow you to handle multiple connections simultaneously. Key concepts. FCNTL, change file status flags. Used to set the O_non-block flag on a socket. Select, /poll, /epoll, I/O multiplexing. Monitor multiple file descriptors, including sockets, for readability, writability, and errors. Error no equals egain or error no equals would block. Indicates that a non-blocking operation would have blocked. Your code must handle this gracefully. Code example, C, non-blocking socket with select. Explanation. 1 FCNTL, server_FD, F_set flow, flags O_non-block, sets the server socket to non-blocking mode. 2 Select, monitors multiple sockets for activity. Select, blocks until one or more sockets are ready for reading, writing, or have an error condition. 3 FD_0, FD_set, FD_reset macros for manipulating the FD_set. 4 Accept, in the select loop, if the server socket is ready for reading, i.e., a new connection is pending, accept is called. Crucially, we check for egain or would block after calling accept. These errors indicate that no connections were immediately available. 5 Read/send, inside the loop, we check each connected socket to see if it is ready for reading. If it is, we read data from it. We then echo the data back. Read can also return egain and would block if there is nothing to read right now. 6 Error handling. Robust error handling is essential. We check for errors after socket, bind, listen, accept, read, send, fcntl, and select. Poll, and epoll, asterisk. Asterisk poll is a more scalable alternative to select, especially when dealing with a large number of file descriptors. Asterisk epoll, Linux specific, provides the most efficient mechanism for I/O event notification in many cases. It uses a kernel data structure to track file descriptor status. Example, C, using poll. Key improvements with poll, asterisk. Asterisk struct polth asterisk. The polth structure simplifies the code by associating a file descriptor, FD, with the events you want to monitor, events, and the events that actually occurred, revents. Asterisk scalability asterisk poll is generally more scalable than select, especially for a large number of file descriptors, as it doesn't have the FD_set size limitation. Asterisk event handling asterisk. The events field indicates the events that have occurred on the socket. We check for pollen, readable, poll hoop, hang up, example client closed connection, and polar, error condition. Epoll, Linux specific. Epoll is the most scalable I/O event notification mechanism on Linux. It's significantly more efficient than select, and poll, for large numbers of connections. Here's a simplified outline of how to use it. 1 epoll_create, asterisk creates an epoll instance, an epoll file descriptor. 2 epoll_ctl, asterisk adds, modifies, or removes file descriptors from the epoll instance. You specify the events you're interested in, example epollen, epollout. 3 epoll_wait, asterisk waits for events to occur on the file descriptors in the epoll instance. 4 process events asterisk when epoll_wait returns, it provides a list of file descriptors that have events pending. Important notes about epoll, asterisk. Asterisk edge triggered versus level triggered asterisk. Epoll can be configured for edge triggered or level triggered behavior. Edge triggered mode provides higher performance but requires careful handling to avoid missed events. Asterisk epoll shot asterisk. This flag can be used to ensure that a file descriptor is only notified once until you rearm it. It's useful in multithreaded/multiprocessing scenarios to prevent multiple threads/processes from handling the same event. Asterisk epoll wrote up asterisk detect when the other end closes the connection. Important for handling socket closures gracefully. 2. Multithreading and multiprocessing. Asynchronous I/O is excellent, but CPU-bound tasks can still block the event loop. Multithreading and multiprocessing allow you to offload these tasks to separate threads or processes, improving concurrency. Multithreading, see with threads. Explanation asterisk. 1 thread_create, asterisk creates a new thread to handle each client connection. 2 thread_detach, asterisk detaches the thread. Detached threads automatically release their resources when they terminate. Without this, you'd need to thread_join, each thread to prevent memory leaks. 3 thread function, handle_client, this function handles the communication with the client. It reads data, processes it, and sends a response. 4 passing data to threads asterisk we allocate a client_data structure on the heap to pass the client socket descriptor to the thread function. This is important because the accept call in the main thread might be followed by another accept call before the thread gets a chance to use the new _socket value. Important asterisk free this allocated memory in the handle_client thread after closing the socket to prevent memory leaks. 5 thread safety asterisk ensure that any shared resources, example global variables, data structures, are protected with mutexes or other synchronization mechanisms to prevent race conditions. Multiprocessing, see with fork. Explanation asterisk. One fork, asterisk creates a new process. The child process inherits a copy of the parent's address space, including the socket descriptor. To close, asterisk crucially, the child process closes the listening socket, server_FD, and the parent process closes the client socket, new_socket. This prevents resource leaks. 3.